Hello students, welcome back to yet another session in this unit, magnetic refrigeration system. So here it is little bigger topic and I have splitted this into two sessions. Now we will see magnetic refrigeration and its a comparison with conventional refrigeration system we will take up in next session. So these are all the topics we have seen, and now we are going to start the topic magnetic refrigeration system. So in next session also we are going to discuss only magnetic refrigeration system. So here the refrigeration process is the process of removing heat from matter. So from any substance or from any matter, the heat is removed, and that process is known as refrigeration process, which may exist as a solid, liquid or gas. So the matter can be in any of these forms, solid, liquid or gas. The removal of heat from the matter cools it or lowers its temperature. In mechanical refrigeration, a refrigerant is a substance that absorbs heat at low temperatures and pressures and transfers it to the condensing medium. So this is mechanical refrigeration system, and the region of transfer involves higher temperatures and pressures for the refrigerant. So though expansion, compression and a cooling medium such as air or water, the refrigerant effectively removes heat from a substance and transfers it to the cooling medium. So this is the general or conventional refrigeration system process. So societal dependency on refrigeration, almost everybody is relying on refrigeration. So it is a very much essential system in society as well. So society is heavily reliant on refrigeration for cooling technology, and refrigeration is critical to both health and the global economy. So common consumer applications include air conditioning, food preservation, air dehumidification, and beverage dispensing and ice making. And then without refrigeration, food supply would still be seasonal and limited to locally produced non-perishable items. So here, without refrigeration, all these things are not possible. So conventional refrigeration and environmental concerns. So modern refrigeration primarily relies on compression, expansion and refrigeration cycle. So it is reliable and relatively low cost technology. Over the years, all parts of conventional refrigerator have been significantly improved through extensive research and development. However, some refrigerants used are hazardous chemicals. So many chemicals are turning out into refrigerants, and few of them are hazardous to health as well as to environment, and other contribute to ozone layer depletion and global warming. As a result, conventional refrigeration technologies may worsen the environmental conditions and global climate trends. So magnetic refrigeration, so it is one of the unconventional refrigeration systems, but still a very effective system, and it is an emerging technology as well. So magnetic refrigeration offers various advantages over conventional gas based refrigeration system, and they are efficiency, reliability, low noise, environmental friendliness. So this method is considered a promising alternative to replace conventional systems. So conventional systems, we have vapor compression system where different types of refrigerants we are employing, whereas it is this magnetic refrigeration system can be a potential replacement for the conventional system. The development of magnetic material and the use of magnetic refrigeration cycles, magnetic fields and room temperature magnetic refrigerative current, regenerative current, and under investigation. So there are so many research aspects going on, and with which definitely this will be the one of the replacement technology for our conventional refrigeration systems. So coming to history, so initially the refrigeration effect is pure iron was discovered in the year 1881 by E. Warburg. The cooling effect observed varied between 0.5 to 2 Kelvin, that is per Tesla. So that is Kelvin per Tesla. Key scientific advancements took place in the late 1920s, and major advancements occurred when cooling via adiabatic demagnetization was independently proposed by two scientists. So they are DB and Geik. So these two scientists have independently proposed a adiabatic demagnetization process. A few years later, Geik and McDougall used the technique to reach a temperature of 0.25 Kelvin. Cooling technology developments in 1933 to 1997, numerous advances in the utilization of magnetocaloric effects for cooling were made. So here in 1933 to 1997, it is the period where so many advancements took place in refrigeration system, such as magnetocaloric effect came into picture during this period. So here it has become a proof of concept, and magnetic refrigeration proof of concept. In 1997, the first near room temperature proof of concept for magnetic refrigeration was demonstrated by Professor Carl A. Schneider Jr. at the Iowa State University Ames Laboratories. And this event spurred interest from scientists and companies worldwide in developing new room temperature materials and magnetic refrigeration designs. And the magnetic fields used in these experiments ranged from 0.6 T to 10 Teslas, where Tesla is a unit of magnetic field strength. So it is one of the units to measure the magnetic field strength, Tesla. So magnetic fields above 2 Tesla are difficult to produce using permanent magnets and are instead created using superconducting magnets. That is, 1 Tesla is approximately 20,000 times the Earth magnetic field strength. So magnetic refrigeration, overview of magnetic refrigeration. Magnetic refrigeration, also known as adiabatic demagnetization. So this is another name for magnetic refrigeration. Is a cooling technology based on magnetocaloric effect. So MCE, on intrinsic property of magnetic solids. The refrigerant used in this process is typically a paramagnetic substance such as cerium magnesium nitrate. So in this context, the active magnetic dipoles are those found in the electron shells of the paramagnetic atoms, and its working principle: a strong magnetic field is applied to the refrigerant, aligning its various magnetic dipoles. This alignment reduces the degrees of freedom of the refrigerant, thereby lowering its entropy. The refrigerant absorbs heat from the heat sink, which results in the release of heat due to the induction in entropy. And then we have the system's thermal contact with the heat sink is then broken, and the system is insulated. Actually, it is insulated. The magnetic field is switched off, increasing the heat capacity of the refrigerant, which results in a further decrease in its temperature. The cooling effect lowers the refrigerant's temperature below the heat sink's temperature. So this is the working principle. And the magnetic refrigeration limitations and applications. Few materials exhibit the necessary properties for magnetic refrigeration to be used effectively at room temperature. So therefore, current applications of magnetic refrigeration are primarily limited to cryogenics and research contexts. So objectives of magnetic refrigeration. So the goal is very simple, to develop more efficient and cost effective small scale H2 liquefiers as an alternative to vapor compression cycles using magnetic refrigeration. So hydrogen storage. So magnetic refrigeration can help solve the problem of hydrogen storage at very low temperatures. The Hydrogen Research Institute (HRI) is studying this process with the aid of magnetic refrigeration to provide cooling of hydrogen storage by liquefying it. So hydrogen liquefaction. Hydrogen can be liquefied at a low temperature, which is achieved using magnetic refrigeration. So magnetic liquefier. So magnetic refrigeration also provides a method to store hydrogen by liquefying it, and it is further used for purpose is called a magnetic liquefier. So magnetocaloric effect. So this is a very important factor or a very important concept in magnetic refrigeration system. So that is MCE. And MCE, magnetocaloric effect. MCE from magnet and calorie is a magnetothermodynamic phenomenon where a reversible temperature change of material occurs when it is exposed to a changing magnetic field, and it is also known as adiabatic demagnetization in low temperature physics due to its application to produce temperature drop. So refrigeration process, it is in the overall refrigeration process, a decrease in the strength of an extremely applied magnetic field causes the magnetic domains of material known as magnetocaloric material to become disoriented by the agitation of thermal energy. So they are known as phonons. So if the material is isolated such that no energy migrates into the material, so that is an adiabatic process. So it plays an adiabatic process. The temperature of the material drops as the domain absorbs thermal energy. So here the randomization of domains. The domains randomize similarly to how ferromagnetic materials behave at Curie temperature. However, in MCE, the magnetic dipoles overcome a decreased external magnetic field while thermal energy remains constant. So examples are, one of the most notable materials exhibiting the MCE is gadolinium and its alloys. So gadolinium's temperature is observed to increase when enters a magnetic field and returns to normal when it leaves the magnetic field. The effect is stronger, and gadolinium alloys like GD5, that is Si2, Ge2, and compound like PrNi5, that is parasodium allied with nickel, shows a very strong MCE, allowing it to reach near absolute zero temperatures. And here this alloy provides a very good cooling effect. Adiabatic magnetization. This phenomena is also known as adiabatic magnetization. And working principle, here you can see the material magnetized, and here this becomes a hot, and this is a thermometer kept, and is measured between this. So this is magnetic material kept between these two poles, north and south poles, and this is when demagnetized, it remains cold. It remains cold, and magnetic material remains cold, and this is out of this field, magnetic field. And this is the simple working principle of magnetic refrigeration. So here the magnetic field application as shown in the figure. When magnetic material is placed in magnetic field, the thermometer attached to it shows a high temperature as the material temperature increases. So temperature reduction is done. Conversely, when the magnetic material is removed from the magnetic field, the thermometer shows a low temperature of the material temperature decreases. And the cycle of operation and material magnetized in the presence of magnetic field, the material's temperature increases, and material demagnetized upon removal from the magnetic field, the material temperature decreases. So this is what we observed in the earlier diagram, and the cooling process taking place to cool a desired place. The magnetic field is applied to the material in the place. As the temperature increases, the material temperature increases, it absorbs heat from the surrounding area. By removing the magnetic material from the field, it will lose heat and the cooling continue, and the temperature continue cooling the desired place. So here the desired place will be cooled when the material is removed from the magnetic field. So system components, the magnetic refrigeration system consists of two beds containing spherical power of gadolinium, which is used with water as the heat transfer fluid, and magnetic field of this system is 5 Weber per meter square, which provides a temperature span of 38 Kelvin, and the heat transfer fluid, a mixture of water and ethanol, serves as the heat transfer fluid of the system, and the fluid passes through the hot heat exchanger, which uses air to transfer heat to the atmosphere. The fluid then passes through the copper plates attached to the non-magnetized cooler. Magnetocaloric beds loses heat as it moves through. A fan blows air over the cold fluid in the freezer to maintain the freezer's temperature at approximately 0 degree Fahrenheit, and the fluid then gets heated to up to 80 degree Fahrenheit as it passes through the copper plates, and the magnetized warmer magnetocaloric beds, where it continues to cycle through the local magnetic field. And this is the magnetic bed and bed movement. The magnetocaloric beds simultaneously move up and down. So this is the diagram. So here this is the electromagnet and hot heat exchanger. So cold magnetocaloric beds. So these are cold magnetocaloric beds, and these are hot magnetocaloric beds, and this is the drive shaft and the cold heat exchanger. And the magnetocaloric beds simultaneously move up and down into and out of magnetic field. The second position of the beds is shown in figure. The cold air from the freezer is blown into the refrigerator by the freezer fan. The temperature of the refrigerator section is kept around 39 degree Fahrenheit. So this is a simple arrangement of magnetocaloric effect and its bits. Refrigerator configuration. The typical household refrigerator has an internal volume of 165 to 200 liters, where the freezer represents approximately 30% of this volume. And freezers are designed to maintain a temperature of 0 degree Fahrenheit, while refrigerators maintain a temperature of 39 degree Fahrenheit. And insulation is the refrigerator is insulated with polyurethane foam, which is one of the most common forms of insulation available, and this is commonly used material, polyurethane foam. And the refrigerator is kept cool by forcing cold air from the freezer into the refrigerator using a small fan. So control system here, the control system for maintaining the desired internal temperature consists of two positions with on off switches. The freezer thermostat regulates the temperature by turning the compressor off and which allows the temperature below 0 degree Fahrenheit. The second thermostat regulates the fan that cools the refrigerator to 39 degree Fahrenheit. So heat transfer fluid, and the heat transfer fluid for the magnetic refrigeration system is a liquid alcohol water mixture with 60% of ethanol and 40% of water. This mixer has a freezing point of minus 40 degree Fahrenheit, ensuring it doesn't freeze at operating temperature. And this mixer is cheaper than traditional refrigerants and also reduces environmental damage caused by other refrigerants. So fluid cycle here, the fluid temperature in the cycle ranges from minus 12 degree Fahrenheit to 80 degree Fahrenheit. The heat transfer fluid initially at 70 degree Fahrenheit is cooled to minus 12 degree Fahrenheit by the non-magnetized cold set of beds. This cooled fluid is then sent to the cold heat exchanger, where it absorbs excess heat from the freezer, cooling it down to 0 degree Fahrenheit. The warmed fluid then flows through the opposite magnetized set of beds, where it is cooled to with the temperature to 80 degree Fahrenheit. So this hot steam is then cooled by air at room temperature in the hot heat exchanger. The cycle repeats every 3 seconds at the beds switch positions. So here very fast cycle is happening here, and the cycle repeats at every 3 seconds at the bed switch positions. And copper tubing is used throughout the loop to connect the heat exchangers. So then the magnetocaloric beds, there are two sets kept. The two sets of beds contain small spheres of magnetocaloric material. The beds are alternated in and out of the magnetic field using a drive shaft that rotates them while still keeping them in contact with the heat transfer plates. So fluid movement, the cycle ensures that the temperature of refrigerant fluid maintains its flow through the system, keeping the desired sections of the refrigerator and freezer within their required temperature ranges. So magnetic refrigeration cycle here, the principle of magnetic refrigeration. The magnetic refrigeration is primarily based on the magnetocaloric effect, where materials change temperature when they are magnetized and demagnetized. Adiabatic application of a magnetic field reduces the magnetic entropy by aligning the magnetic moments of the material. This results in an increase in the material's temperature. This phenomena is reversible for some materials. When the magnetic field is removed, the entropy increases, cooling the material accordingly. And the reversibility and work recovery properties of magnetic refrigeration make it a potentially more efficient process than conventional gas compression expansion refrigeration cycles. So here this is the diagram, and magnetic refrigeration can be 50% more efficient than conventional refrigerators. And you can see here magnetocaloric effect. So here this is the apply magnetic field and remove magnetic field, so cyclically happening here. So when you apply, and these ions are in fine nature, and there will be entropy increase upon removing the magnetic field. So this is how magnetocaloric effect is working here. So magnetic refrigeration cycle, the process is performed as a refrigeration cycle similar to the Carnot cycle, and it starts with the introduction of working substance refrigerant into a magnetic field, increasing the magnetic flux density. And the working material is the refrigerant, which starts in the thermal equilibrium with the refrigerated environment. And types of thermodynamic cycle here, The cycle of magnetic refrigeration consists of the following steps: adiabatic magnetization, isomagnetic enthalpy transfer, and adiabatic demagnetization, isomagnetic entropic transfer. So the first one, adiabatic magnetization. So here the first step of the cycle, a magnetocaloric substance is placed in the insulated environment. So effect of magnetic field, and the magnetic field is applied, that is plus H, causing the magnetic dipoles of the atoms to align, and which increases the magnetic material's magnetic entropy and heat capacity. So since overall energy is not lost, the total entropy does not decrease. The result is that the material's temperature increases by T plus delta T adiabatic, and this is how happening. So this is vapor compression, and this is magnetic compression, and here the heat, this is plus adiabatic process, plus H is added, and minus Q, that is heat is removed, and here the H during adiabatic process the H remains 0, and when the delta T adiabatic is removed and the heat energy is added here, and now the final magnetic temperature, magnetic refrigeration is taking place here by increasing the entropy of the ions. So magnetic refrigeration cycle versus vapor compression, vapor cycle refrigeration, and the magnetic refrigeration cycle is similar to the gas compression and expansion cycle used in regular refrigeration, and the steps are analogous to the Carnot cycle involving adiabatic process and enthalpy entropy transfers. So isomagnetic enthalpy transfer. So here heat addition is taking place. Heat is added to the material which can be removed by fluid like water or helium, and the magnetic field is held constant to prevent the dipoles from reabsorbing the heat, and cooling the material. After sufficient cooling, the magnetocaloric material and the coolant are separated, and the material returns to H equal to 0. And adiabatic demagnetization, so cooling the material, so the substance is returned to an adiabatic insulated condition, ensuring total entropy remains constant, and the magnetic field is decreased, so that becomes minus H, and thermal energy causes the magnetic moments to overcome the field, resulting in cooling due to adiabatic temperature change, and this phase results in the transfer of energy from thermal entropy to magnetic entropy. So disorder of magnetic dipoles. So isomagnetic entropic transfer, heat migration. The material is placed in thermal contact with the environment being refrigerated, and the magnetic field is held constant to prevent the material from heating back up, and heat transfer, because the working material is cooler than the refrigerated environment, heat energy migrates into the working material. So equilibrium, once the refrigerant and refrigerated environment reach thermal equilibrium, the cycle continues. So here these are the processes taking place, and we have seen the small between the vapor compression system and refrigeration system, magnetic refrigeration system. So both are very good systems, no doubt, and we will see more about magnetic refrigeration system, that is in next session, and I am continuing the same topic in next session also, students. We will see the complete details of magnetic refrigeration, the remaining details of magnetic refrigeration system in our next session. So we stop here, and coming to our textbooks, so you can refer all these books. So first one is CP Aurora, where you can find magnetic refrigeration, as well as in Rajput. In both books you can refer. And Rajput, I have taken from Rajput as well as Kurmi. These two books I have used to prepare this material, and definitely you can refer these two books. The soft copy of these books also I have given you in Google Classroom. So please refer these two books, and I am also uploading the notes on this in the Google Classroom. Also you please refer the notes. And apart from that, we have these references. So Ashray handbook, this soft copy also I have given you. Air conditioning, this is a good book on air conditioning. And workload, that is the load calculations, we are going to refer that book. And Kurmi, in this book you can always refer. It is a very simple and easy book to understand the concepts. So here we will stop. So let me say thank you, students. And in next session we will meet again. We will complete the magnetic refrigeration system completely, and we will wind up this topic. Thank you, students. Thank you.